talked about in the last lecture is saying, well, suppose we're integrating and our domain is something really simple. So our domain down below is a rectangle. So we have x went from a to b and y went from c to d, and we're like, okay, well, that's easy enough for us to do. But what if our region is not a rectangle? So suppose I have my surface up here. So the surface up here is some function z equals f of xy, but it's not sitting on top of a rectangle. Maybe it's sitting on top of some other shape, maybe something that looks a little bit like an ellipse, or it doesn't have to be. It can be any shape I want. Now, what do? And the answer won't surprise you. We do the same thing that we did before, because really that's what happens in math is you have one good idea and then you just enhance over and over again. Now, what's our idea? Well, we slice things up and understand each part. So again, same philosophy. We're going to slice things up, look at each slice, add to get the total. That's what integration is. Now, when we slice, there's two ways to slice if we're talking about a two-dimensional region. So here, I'm looking at the xy plane. So the xy plane, that's this part down below, and I'm saying, what does this domain look like? Well, if I take a slice and I slice it in the xy plane vertically, so that would be this slice over here, well, what is happening? Well, I'm going between two curves. So what do I have? I have a bottom curve, y equals phi1 of x. So that's the curve on the bottom. I have a top curve, y equals phi2 of x. And now what I say is, all right, given that I'm at a particular x, so here's my particular x value, y is going to go from phi1 to phi2. So what do I do to find the total of everything? Well, I'm going to add up what happens on the slices. And for each slice, I go from phi1 of x to phi2 of x. So my bounds now depend on the outer variable. So the outer variable, when I talk about that, that's integrating with respect to x. So the bounds can depend on x. Perfectly fine. So I'm integrating from phi1 to phi2, f of xy dy. And there's a note which says, look, if you integrate this, what happens? Well, you're integrating out with respect to y. So once you integrate with respect to y, and then you evaluate between phi1 of x to phi2 of x, what's left is going to be just a function only of x. So each time that we do a layer, we go through and work through the process, we're going to eliminate one variable. So initially we start out and we have this f of x comma y. It depends on both x and y. After we integrate one time, we're going to get rid of the y's. And then we're just going to have only x's. And then once we integrate with respect to x, then we're only going to have a number. That's our number. That's our total. That's what we're after. Now, I said there were two ways to slice. The other way to slice is horizontal. So what happens there? Well, I go between the left-hand curve to the right-hand curve. So on the left, I have some function, I'll call it psi1, to some other function, psi2. And what happens? Well, it's the same philosophy. Now what's happening is we're going to add up our slices, and where we slice horizontally. So the total is an integral of the c to d, the value of the slice dy. Well, where do you find the value of the slice? Well, it's an integral psi1 of y to psi2 of y, f of xy dx. All right, so in other words, what you can think of is when I'm talking about this inside integral, I'm at a particular choice of y. So this slice isn't just any slice, it corresponds to some fixed value of y. And I'm just saying, what's the total if we add these all up? But again, the same philosophy. Once you integrate on the inside and you evaluate, you'll get rid of all the x's, and what's left is something only in terms of y. All right, so that's not so bad. It's really not that much different from last time. We just get a little bit of extra bookkeeping, but not too much. So let's do a quick example. Let's just do one of these integrals. find the integral from 0 to 1 of the integral from x squared to square root of x of x squared plus y squared dy dx. All right. Well, to start, we remember that integration, especially multivariable integration, it's like an onion. There's layers to this. You just go through one layer at a time. And like an onion, there might be a few tears. But the inner part. Okay, first we're integrating with respect to y. So when we're integrating dy, and that's what that's telling us, we're saying, okay, everything that's not a y, we're treating like a constant. So I'm still doing the same techniques of finding antiderivatives to do our evaluation. And it's just similar to the last part of the course where we talked about differentiation. We said, oh, just treat all the variables as constant except the one you care about. It's the same thing here. We're going to treat all the variables except the one we care about as constants, and the one we care about is the y. So what is the antiderivative of x squared plus y squared with respect to y? It is x squared y plus y cubed over 3. Now, I evaluate with respect to y I'm going to evaluate. Now, to help me remember that I'm evaluating y, I'm going to put y equals x squared to y equals root x. Because every time we write down these integrals, it's sort of a suppressed notation. So when we talk about this root x, it's not just root x, it's y equals root x. And this x squared, it's y equals x squared. All right. Well, the next step is, of course, do the evaluation. So 0 to 1, x squared times square root of x. That's x squared times square root of x, which we can write as x to the 5 halves. Then plus 1/3 square root of x cubed, x to the 3 halves. Then we have subtract x squared times x squared, x to the 4th. And then subtract again, 1/3 x squared cubed will become 1/3 x to the 6th. All right. Well, good. That's our layer. We integrated and evaluated. And notice that what we're left with now, only in terms of x, which is what we should expect. Okay, now what do we do? Integrate again. Absolutely. So, integral x to 5 halves? 2/7 x to 7 halves. Plus, well, integral of 1/3 x to the 3 halves? 2/15 x to the 5 halves. Integral of x to the 4th? X to the 5th over 5. 1/3 x to the 6th. And x to the 7th, and then in front, 1/21. Evaluate from 0 to 1 equals 2/7 plus 2. See, 0 to 1, our favorite numbers to evaluate. Because when you plug in 1 to any power, it's 1. And 0 to any power is 0. All right, so 2/7 plus 2/15 minus 1/5 minus 1/21. Now, what can we do here? Yeah, we could probably put a box around it if we were not brave. But if we were being brave, what could we do? Still put a box? Yeah. We're brave enough to say we don't know our arithmetic skills. Okay. Well, that's a different kind of bravery. Common denominator here is actually not too bad. It's 105. And so what do you get? Well, the first one, you have to multiply by 15, which would give us 30. The next one you have to multiply by 7, give you 14. The next one would be 21. And the last one would be 5. And let's see, so that's 44 minus 26. 18? Yes? Yes, good. 18 over 105. But wait a second, 18 and 105, they have something in common. They both have 3 in common. So that becomes 6 over 35. There you go. That's not so bad. Now, on a side note, we talked about understanding the bounds, and notation is important. It really becomes important. I know we gave you a hard time about it in Calc 1. We gave you a hard time about it in Calc 2. It's like, keep track of notation, keep track of notation. It's because of Calc 3. You really, really have to keep track of notation. So when we talk about things, you know, the integral from a to b, integral from some function of x to some other function of x, remember that really when we talk about a to b, and there's a dx, because we tie the outside integral with the outside d something. So it's really x equals a to x equals b. And the inside, okay, it's really y equals v1 of x, y equals v2 of x. So it's important to understand how these things connect together. And in particular, one thing that you'll see is that I can take my bounds now and I can actually describe it. So I say, oh, x is running from a to b, and I can see that y is running between phi1 of x and phi2 of x. Now, something that you should hopefully spot here is what's happening on the outer integral. So when I look at the outside integral, this a to b, this involves numbers. So in other words, I'm going from a number to a number. And then when I go to the next integral, phi1 to phi2, that's not numbers anymore. These are curves. So as you build up your integrals, the outer integrals are numbers. The next layer, curves. On Monday, we're going to go another layer. Well, that's Monday. So we'll talk about that then. All right. Well, so let's take that and let's actually try it. Because one of the things is we haven't drawn a picture. Where is this integrating over? Can we figure that out? So let's figure that out. Integral 0 to 1, integral x squared to root x squared plus y squared, dy dx. Well, we read it off. Where does x go from? 0 to 1. So we can see where x goes from. Where does y go from? X squared to square root of x. So now, if we want to sketch, well, we just start drawing the curves. So we do them sort of one at a time and just say, okay, x squared is less than or equal to y. We'll start by drawing the curve x squared equals y, also known as y equals x squared, which is what? Parabola. All right, and now the other side, y is less than or equal to root x. Well, say just y equals root x, which, what does y equals root x look like? Yeah, it's actually a parabola on its side. Now, that's the two curves. So we had the y equals x squared, the y equals square root of x, and now we're told x goes from 0. Well, that's easy to spot. That's the origin, to 1. Well, it turns out y equals x squared and y equals square root of x, they have a point in common. And that point in common happens to be 1. Because if you take 1 and square it, or if you take 1 and take the square root, you're still going to get the same value. So if we let x go from 0 to 1, and y go from x squared to square root of x, our region is this part right here. So that's our region that we're integrating over. So if you have an integral, you can say, okay, what's the region? Now, of course, we want to be able to get to another stage, which is, suppose I have the region, what are the bounds? Well, to get to that, you sort of work backward and say, okay, if I want to figure out the bounds, I look and say, where do my curves go from? And where does y range between? What two curves? Then where does x range between? What two numbers? Of course, that's one way. This is slicing vertically. Well, maybe we want to slice horizontally. That's another story. Okay, a little bit more practice. So sketch the regions associated with the following integrals. All right, so there's two different integrals here, and let's see what they look like. So let's talk about our bounds. So first off, our outer limit is the next. So what does this say about x in the first integral? it goes from 0 to 2. All right, what does this tell me about y in this integral? 0 to x squared. Okay, well then, that's not so hard, because I know how to draw y equals 0. Y equals 0 is this curve. And y equals x squared, I know how to graph that. That's a parabola. Y equals x squared. And I'm going between these two. And then I'm going to start at x equals 0, and I'm going to go until I get to x equals 2. All right, and notice that I'm going, x goes from 0 to 2, and then that y is going between these two curves. So I'm taking this region here, and I'm slicing in a nice horizontal fashion. Okay, so that's that integral. Well, let's look at the next integral. It's a different integral. So here, notice different order of integration. Wait, whoops, it's supposed to be, is it? Yeah. Did this mess up? Oh, this is wrong. Should have been x. Ah! No, that should have been y. No, that's fine. What is it here? This should be x, and that should be y. Okay, something's wrong. Now, you might say, how do you know? Well, really, after I integrate out, well, okay, we'll get to y later on. Why did we spot? Okay, we'll fix it in post-production. All right. So, with the correction, where does y go between? 0 to 4. And I like to actually, when I'm trying to understand something, I like to work from the outside in. Some people say, work from the inside out. No. Outside in. That's the better way. Okay, where does x go between? Square root of y and 2. Now, let's sketch that. All right, so we have these two curves. Square root of y equals x. What does that look like? It looks a lot like y equals x squared. So this is x equals square root of y. X equals 2, well, that looks like that curve. And now, where are we going? Well, y goes from 0 to 4. Now, it turns out that y equals 4 is right here. So if I'm going, y goes from 0 to 4, then x goes from square root of y to 2, I'm going to be slicing the region horizontally. Now, the real point of this question, what's happening with these two regions? They're the same region. So what's going to happen with these two integrals? They're the same value. So we're going to get the same answer if we knew whatever f is. Now we don't know f, so we don't know what the answer is. But if we did, we'd get the same answer. Now, you should probably notice something. A priori, in other words, from the beginning, it's not so clear that these are the same. Now, we're used to in the last lecture to say, oh, it's so easy to switch the bounds. You just sort of, whoop, where do you, oh, here, I'll do it, whoop, like that, you know. Instead of A, B, C, D, you're like, oh, C, D, A, B, no problem. No, switching bounds, once you have interesting functions sitting there, it gets subtle. Or, as we like to say, it gets more fun. So how do you switch bounds? All right. So when you're talking about changing order of integration, I want to go, instead of an integral dy dx, I want to go dx dy. So we have to do a couple of things. Now, they're pretty intuitive. In fact, a lot of them are things we've already been doing. So the first thing is to say, what are the current bounds? And how do we get the current bounds? They're stored in the notation. So the current bounds are stored in these integral symbols. These are where the current bounds are stored, and we can write down what the current bounds are. Now the next step will challenge us a little bit on some problems, hopefully not too much, is to draw a picture. So we will say, look, once I have a bound, I can go from bounds to picture. Okay, that's not hard in either case. In fact, it's not hard to go in either direction, really. So I have bounds, I can get a picture. And now once I have a picture, I say, well, make sure you can label all the curves. So for instance, here, on this one, I can say, there's this curve. Well, I can label this as x equals 2. And this curve, I can label as y equals 0. And this curve, y equals x squared, well, I can also label it as x equals square root of y. So it's that ability to say, oh, let me rewrite it in terms of the other variable, essentially doing inverse functions really here. Now, the fact that we need to be able to do inverse functions means we're going to be given fairly simple curves to work with, and that's okay. We don't mind that. So that's the third step. And then it says, hey, once you've done step 3, just reverse. In other words, go back from the picture to your bounds. So in other words, suppose I just had the picture. Well, what you need to do is remember, how are you slicing? Because there's two ways to slice. You start slicing one way, horizontal or vertical. Now you're going to slice the opposite way, vertical or horizontal. And once you understand how you slice, you say, okay, what are the curves which bound? So if I said, I know I'm slicing horizontal now, I say, well, my bounding curves are the x equals 2 and the x equals square root of y. Okay, and then I say, well, great. Now, where do you start and stop taking your slices? Well, I start down here at the bottom, that's 0, and I stop up here, and that's at 4. And now I have my bounds. Now, a side note, because a lot of people are very comfortable with slicing vertically, not so much with slicing horizontally. Always remember, orientation matters. So, what do I mean by that? When you're slicing vertically up down, it's always the larger values on the top, the smaller values on the bottom. So it's high minus low. Follow the orientation. High value minus low value, top minus bottom. When we're slicing horizontally, we still want to take high, subtract low. High is towards the right. Low is to the left. So the high value is on the upper part. So the high value is upstairs, and the low value is downstairs. So keep that in mind. The last comment down here we've already mentioned. The outer integral should always go between numbers. The inner integral should go between curves. Okay, well, let's try it. We know the theory. What's the practice? Change the order of integration for the following integral. Integral from -1 to 0, integral negative square root y plus 1 to positive square root y plus 1. All right. Do you remember our steps? What do we start doing? Now write down what's the current bounds. What is this integral asking us to find? So the current bounds, what do we have? Well, the outer integral is attached to the y. So what do we know about y? -1 less than or equal to y less than or equal to 0. I can read off the bounds. Okay, now go to the next layer in. This is an x layer because there's the dx. What's true about x? Negative square root of y plus 1 less than or equal to x less than or equal to square root y plus 1. So once you start doing these, you see certain patterns. Oh, okay, -1, 0 does the upper and lower, and then the y goes in the middle. And here, negative square root y plus 1 to positive square root y plus 1, and x is in the middle. Okay, so there's my bounds. All right, so we've written down our bounds. Okay, well, what comes next? We should draw a picture. All right, reach in and connect with your inner artist a little bit. Now I like to draw the curves. So let's think about these curves. Suppose I look at this curve. X equals square root of y plus 1. Well, maybe I'm not so clear about what that curve looks like. Is there another way to write this curve? Well, x squared equals y plus 1, or x squared minus 1 equals y. So I say, aha, now that's the curve I can get behind. because it's a parabola, we've done one thing to it. What have we done to our parabola? Shifted it down. So we've shifted it down. Now it turns out that if I'm looking at x equals the square root of y plus 1, well, that's always going to have a positive x value, so it's the right-hand side of the parabola. On the other hand, if I were on the left-hand side, that would be x equals minus square root of y plus 1. Okay, now this parabola is also y equals x squared minus 1. We should label everything. Let's think about what happens for y. Well, where does y go from? We start where? Negative 1, which is here. And notice right now, because the inner function, the inner integral, is going from a function x to function x, which means right now we're slicing horizontally. So we're slicing between our lower curve and our upper curve, or I should say a low value, high value. When do we stop? At 0. Okay, so that's our region. It's sort of the bottom part of a parabola. Good. Now, what do we want to do? Well, we're actually making great progress. Where are we at in our process? We've written the bounds, we drew a picture. It's useful to indicate how we slice, so it's like, okay, currently we're slicing horizontally. We've labeled our curves. Well, almost. Which curve haven't we labeled yet? Yeah, this curve right here. That hasn't been labeled yet. But that's y equals 0. That's an easy one to label. And now, use the picture to determine how to break into parts and what the bounds are. Okay. Now, to figure that out, we're going to think about how we slice. We were slicing horizontally, so the next thing we'll do is we're going to change. So we're going to slice vertically. So it means we're slicing this way. Toon, toon, toon. All right. So we have to start and think about a few things. Well, where do we start slicing? Over here. Well, that's when x squared minus 1 equals 0 is at either negative 1 or positive 1. So we start slicing at negative 1. Where do we stop slicing? 1. So our slices are going to go from negative 1 to positive 1. Okay. Now, what about y? Well, that says where am I going between? What's the high point, or the top? 0. What's the low, or the bottom? So it's this curve. What is this curve in terms, y is a function of x? It's x squared minus 1. So now, that's the bounds of my region if I express it in terms of slicing the other way. So the last thing, of course, is once I have these bounds, I can rewrite the integral. I just basically read it off. So the outer part goes from negative 1 to positive 1. That's dx. The inner part goes from x squared minus 1 to 0, and that's dy. And I still have the same function. I don't change the function, I'm just changing the way I describe the region. And that's the way to change the order of integration. Okay. Any questions about how to change the order of integration? Well, then the next question is, why do we change the order of integration? Other than it seems like a really great way to stump you on a test. Is there any reason why we'd want to change the order of integration? And the answer is, there's great reasons why we want to change the order of integration. Because occasionally we'll run into things that we can't integrate as given. So what can happen is by changing the order of integration, we would say, aha, maybe now we can make progress. Or maybe not, but it's worth the try. So if you're stuck, try changing the order of integration. So here's an example. Find the following integral by first changing the order of integration. Now, I can ask the question, how do we know that we should change the order of integration? Well, this one says, because it tells you to. Okay, that's one hint. But suppose there wasn't that hint. Let's look at this problem. Suppose I just say, change the order of integration. That's not me. I'm not that person. Well, all I have to do is integrate e to the y squared dy. How hard could that be? And it turns out very hard. Really, really hard. So hard, you can't do it. Not because I think you're not good, it's just because nobody can do it. It's one of those functions that doesn't have a nice antiderivative. Okay, so that's a kind of a bummer when it comes to solving this problem. So we're like, okay, I can't integrate e to the y squared with respect to y. That's too hard. However, I do claim you can integrate e to the y squared with respect to x. How can you integrate e to the y squared with respect to x?
E to the y squared is a constant when you're integrating with respect to x.
Yeah. See, if I integrate with respect to x, it's really, really easy because e to the y squared is just a constant. So it's e to the y squared times x. Okay, so it's like I can at least integrate with respect to x. But in order for me to integrate with respect to x, I have to change the order of integration. So I can't integrate with respect to x first until I change that order. Okay, so I did. If I can change the order of integration, at least I can make a little teeny tiny bit of progress. So we go through the process to get to that point. All right, so this is going to be something, something, e to the y squared dx dy. All right, that's where we're going to get up to. So, okay, let's draw our picture. What's true about x? X goes from 0 to 4. What's true about y? Goes from a half x up to 2. Now, y equals 2. That's a pretty simple curve. It looks like this. It's a flat line. Y equals a half x. It's a slope of a half. And x equals 0 is over here. And by great coincidence, x equals 4 happens to be where the curve y equals 2 and y equals a half x comes together. Well, it's actually not a coincidence. We planned it that way. But we'll pretend like it's a coincidence to make it be like, ooh, wow. Okay, so this is our region. Currently, how are we slicing our region? We're currently slicing this way. So x goes from 0 to 4. And so for every value of x, I'm going between the two curves for y. Now we're going to switch the order of integration. So now we're going to be slicing horizontal-like. So that's where we want to get to. All right, so we need to identify a few things. Let's see, what do we need? Well, we probably need this curve here. What is that curve? X equals 0. And this curve, currently, we had it as y equals a half x. But we should also write it in terms of x equals. So if y equals a half x, what is x? It's 2y. All right, so now we can start reading things off. So if I'm slicing horizontally, where do I start my slices? Where do I stop my slices? 0 and 2. I start slicing here at the bottom of the region. I stop slicing at the top of the region. 0 to 2. Okay, now, my slices, where do I go from? Well, I go left to right, low to high. So I start where? 0, and I end 2y. All right, so we changed the order of integration, and now we're like, well, at the very least, if nothing else, we can at least integrate one layer. Because, as we said a moment ago, this becomes 0 to 2 of e to the y squared times x. I'm going to evaluate from x equals 0 to x equals 2y dy. Well, we evaluate. And if we evaluate, what will we end up with?
E to the y squared.
Well, e to the y squared times 2y. And then 0, well, that's very convenient. It disappears. Now, we can't integrate e to the y squared. But we no longer have to integrate e to the y squared. Now we have to integrate e to the y squared times 2y. We've added even more stuff that we have to integrate. Can we do it? Yeah, we can do use substitution. In fact, this is a use substitution that we would hope you can probably do in your head now. What is the antiderivative of e to the y squared times 2y? e to the y squared. This is e to the y squared evaluated from 0 to 2, which becomes e to the fourth minus e to the 0, and e to the 0 is 1. All right, good. Bum, ba, bum, ba, bum, ba, ba, bum, ba, bum. Wow, so many great examples. Okay. So, next note. Suppose our region is complicated. Well, that can happen. If it is complicated, break it up into parts and work on each part. So here, we're actually not given bounds. We're just told our region. And we're said R is the region where y is less than or equal to x squared, and 0 is less than or equal to x is less than or equal to 2 minus y squared. And we want to write the integral over the region R, f of x, y, dA, as an iterated integral. Or integrals. Okay, all right. Well, let's start by drawing this region. So we'll put some axes here. So y equals x squared, that's not hard. We know that y equals x squared, that's a parabola. And so we have a parabola going up here. I know that I only need to focus on the right-hand side because of the other restriction. X equals 0, that's not hard. That's the line here, x equals 0. This is the line y equals x squared. And notice that we're below y equals x squared, so I'm underneath y equals x squared. X equals 2 minus y squared. What does that look like?
Parabola opening left moves over 2.
Wow, yes. Good. So, if you're not sure, just build it up. X equals y squared is a parabola. Turn it on its side. X equals minus y squared flips it across the axis. And then if you add 2, that's a shift. So what happens is you shifted it over by 2. So I'm going to come over here, and I'll say this is roughly where 2 is, and then I'm going to open my parabola up this way. Okay, so what's my region? Well, I have to be below y equals x squared, and I have to be between x equals 0 and then this curve 2 minus y squared, which means that my region is this part. Okay, so there's my region. Cool. We should draw a couple of things. Can we find this point where y equals x squared and x equals 2 minus y squared come together? And one thing you should always try is guess a good number. 1 for x or 1 for y? The answer is, why not both? So if you check, 1, 1. Does 1 equal 1 squared? Yes, that means I'm on that parabola. Does 1 equal 2 minus 1 squared? Yeah, which means I'm on the other parabola, which means that this point is at 1, 1. It's almost like they wanted to give us a nice point. Now, the origin, that's easy to spot. That's 0, 0. Where does this point come in? So, what's that? Well, it's when I hit x equals 0 on 2 minus y squared. So, for that, I say, when does 2 minus y squared equal 0? Well, y squared would be 2, so y would be square root of 2. So is that square root of 2? No, that's square root of 2 up there. Plus or minus? That's a minus square root of 2. All right. Now, we were told to write this as iterated integrals. But we weren't told which way to write it. How many choices do we have? We have 2, right? We could do dy dx or dx dy, just as it's a matter of what we want to do. So, which one should we do? Let's do both. We have time. Maybe. Okay. Let's do both. Okay. Dx, dy. Okay. Well, let's phrase it a different way. Do you want to start by slicing horizontally, or do you want to start by slicing vertically? Vertically. That's okay. That's what we're used to. We should start with what we're used to. Now, let's think about what happens. As I come along and slicing vertically, I'm happy. Da, 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 da. Whoa, something happens. Something changed. What happens at 1? The curves change. So below 1, my top curve was this parabola y equals x squared. And after 1, it's this other parabola. Well, what does that mean? Well, whenever you have a bounding curve change, how do you handle it? The answer is we do it twice. So we're going to have 2 pieces. So we will call these pieces piece number 1 and piece number 2. Okay, so let's work through what happens with those 2 pieces. Now, on piece number 1, well, we actually have a little bit more work to do before we can really start. Our little bit more work to do is to label these curves with the other variables. Another way to say y equals x squared is to say x equals square root of y. And the other thing is, suppose I know that x is 2 minus y squared. Well, what if I wanted to solve for y? What would I get? Y squared would be 2 minus x, and then plus or minus square root of 2 minus x. Now, the plus is the top half, so y equals plus square root of 2 minus x. The minus is the bottom half. Okay, so let's talk about our integrals. So we're going to have integral 1 and then integral 2, and then we're just going to add the results together. So for the first integral, where do we start slicing? Because this is a dy dx type integral. dy dx. Sorry, I'm just filling this in. F of xy, f of xy. All right, where do we start slicing? 0. Where do we stop? 1. Because that's between 0 and 1, we have consistently the same curve on the bottom and the same curve on the top. So we're like, that's great. As long as we have that consistency, we can go all the way. What is the curve on the bottom? Negative square root of 2 minus x. What's the curve on the top? X squared. Now, we switch at 1. And we go from 1 to where? 1 to 2. Now, what's the curve on the bottom? It's the same curve, negative square root of 2 minus x. What's the curve on the top? Positive square root of 2 minus x. So we split our 2 integrals, or rather we split our integral into 2, and we choose to split where the bounding curve changes. Now that's if we had integrated dy dx, or in other words, if we made our vertical slices. Maybe it would be better off to do horizontal slices. Well, let's try it. So if I'm doing horizontal slices, that would be f of xy dx dy. So we come along, we start slicing horizontally. It's like everything's great, loving it, and then all of a sudden what happens at 0? My bounding curve on the left changes. See, previously what happened is the bounding curve on the top changed. Now it's bounding curve on the left changed. Well, so if I have a bounding curve change, what do I need to do? We're going to split into 2 integrals. I guess I should choose A and B now, not to be confused with 1 and 2. So we're going to do a part A and a part B, and we're going to add them together. Integral f of xy dx dy. Okay, so let's start. Doesn't matter which order we do it, so let's start here. Where do I start my slicing? What value of y? Negative root 2. And where do I go to? 0. Now, as I make my slice, where's my left and where's my right? 0's on my left. Am I right?
2 minus y squared.
Yes, the 2 minus y squared. And one thing you should think about is, what should I have here? Well, because the inner integral is an integral with respect to x, I should say this should be an x equals something. So x equals 0 to x equals 2 minus y squared. Now, let's go to our next part. Where do we start slicing for the next part? 0. Where do we stop? 1. 0 to 1. All right. Now, what's our bound on the left? Again, it should be an x equals type thing. Square root of y. And the bound on the right? 2 minus y squared. So these two are the exact same. So what we've done is we said we can express this region as the sum of two integrals. And we have to break it up into two because of the shape of our region. All right. Well, we have more questions, but we'll have more time next time. So we'll stop here.